Hello students, good afternoon to all of you. Today I am going to cover the topic that is discrete time Fourier transform. Although it is already done, that is Fourier transform, and why we go for DFT and how DFT is superior as compared to DTFT, and what is the main problem that is encountered with the DFT. And after that I will cover the properties of DFT. So in this present lecture, so I am covering the topic that is DFT, that is the part of our syllabus that is in the fourth chapter of the syllabus signal and system. Now as we know that DTFT, it is the discrete time Fourier transform. So what it is doing, it is transforming the signal from time domain to frequency domain. So when we take the DTFT of any signal xn, that is represented by summation n equal to 0 to infinity xn e raised to the power minus j omega n. Of course, this should be from minus infinity to infinity, but this is the special case of causal signal. Now, we also write this as x omega, but here it is written as x. Actually, it should be r e raised to the power j omega. Now, in this case, r is 1. R is 1, magnitude is 1, so we are writing it x e raised to the power j omega. We can also write it as x omega. That is equal to summation n equal to 0 to infinity xn e raised to the power minus j omega n. So what basically DTFT is doing, it is transforming the signal from time domain to frequency domain. Now the range of digital, because omega is nothing but the digital frequency. So omega varies from 0 to pi and then from pi to 2 pi. So when it repeats one circle, the range is from 0 to pi, 2 pi, and after that it is periodic in nature. So in this case what we see that although the xn is in discrete form, xn is discrete signal, so it is transforming this signal, that is n is time, from time to omega, that is x omega. Omega is basically frequency. So what we see that it transforms the signal from time domain to frequency domain. But the problem here is that the digital frequency, that is omega, its range is from 0 to 2 pi. Its range is from 0 to 2 pi. In this range, omega is continuous. Means such type of signals, when DTFT signals, they are fed to digital systems, they cannot process these signals because they are the continuous function of omega. So this problem is encountered with DTFT because omega is a continuous function of time and it cannot be processed by digital systems directly. So we need to convert this omega into discrete form. So what we will be doing in DFT, we will be covering this range from 0 to 2 pi and we are dividing this into n equal parts. So basically what we are doing, we are discreting, or we are taking samples of this omega at some periodic instants of time. So we are dividing this range into n equidistant samples. So in case of DFT, so the signal produced by or the DFT signal, it can be processed by a digital system directly. Here in this slide also we are having DTFT and IDTFT, inverse discrete time Fourier transform. So in Fourier transform we are transforming the signal from time domain to frequency domain. The time is discrete in nature, whereas the frequency, that is in continuous, that varies from 0 to 2 pi and is periodic in nature. So coming to inverse discrete time Fourier transform, that is given by xn equal to 1 by 2 pi, because we can recover the signal xn from x e j omega, means we can recover the signal xn back from x e j omega by using this expression. So that is xn equal to 1 by 2 pi integration 0 to 2 pi x e raised to power j omega, e raised to power j omega and d omega. So DTFT again, that is x omega, that is equal to summation n equal to 0 to infinity, or we can also write it as n equal to minus infinity to infinity xn e raised to the power minus j omega n. Now coming to discrete Fourier transform. So if we are having a signal xn as given in this slide, that is discrete time signal of length n, then if we want to take its DFT, the DFT of the signal xn, that is represented by capital Xk. Now the n point DFT of sequence xn, that is given by this mathematical expression capital Xk, that is equal to summation n equal to 0 to n minus 1, that is xn e raised to the power minus j 2 pi kn by capital N. Now you note that here the k, it has values 0, 1, 2 and up to n minus 1. So what is the advantage of DFT is that when we take the DFT, the resultant signal, that is also discrete in nature, that is having n distinct points, and such type of signals that can be directly fed to digital systems for further processing. In the previous case, that is DTFT, we note that such type of signals, because they are a continuous function of omega, we cannot fed that signals directly to the digital systems for further processing. So this is basically the advantage of DFT. Now when we are having a signal xn, so what do you mean by the length of the signal? So for example, if xn has 4 samples, means let it be 4 samples are 1, 3, 5, 7. So it is having 4 samples. So what is its length? Its length is 4. Its length is 4. So we can find its DFT, or you may be asked to find its 4-point DFT. So then what is the value of k? K, it changes from 0 to n minus 1. What is capital N in this case? 4. So the values of k will be from 0, 1, 2, 3. Now in this summation also n is equal to 0 to 3, because we are having an input sequence of length 4. So then we are having the summation limits n equal to 0 to 3 xn e raised to the power minus j 2 pi kn by capital N. So this is. Now if we want to find, or we want to recover the signal xn back from xk, so what we have to do, we have to take its inverse discrete Fourier transform. So In this second, we have taken that xn is again the discrete time signal, capital Xk is the endpoint DFT of xn, then the inverse DFT of the sequence xk is given by, that is x small xn, that is equal to 1 by capital N summation k equal to 0 to n minus 1 capital Xk e raised to the power j 2 pi k n by capital N. So small n, it having values 0 to capital N minus 1. So if we compare these two expressions, then we note that in case of DFT, on the left hand side we are having x capital Xk because we are finding the DFT, and in case of IDFT, as we have to recover the signal xn, and on the left hand side it would be small xn. So coming to right hand side, we are having summation, that is from n equal to 0 to capital N minus 1, whereas in case of IDFT it is from k equal to 0 to n minus 1, because DFT is represented by capital Xk, and we have to take the limits of this summation with respect to k. And in the DFT case, because it is xn, because we want to take the DFT of xn, so we have to take the limits of this mission, that is small n equal to 0 to n minus 1. So this is the main difference, and another difference is that in case of DFT there is a negative sign, and in case of IDFT there is a positive sign of e raised to the power, as in the upper case it is e raised to the power means negative same power, and in the lower case, that is IDFT case, it is e raised to the power, that is plus. So this is the major difference between these two expressions. Frequency spectrum using discrete Fourier transform. Now, when we convert the signal from time domain, that is xn, to capital Xk, so what we are having capital Xk, that is in the form of frequency. We are transforming the signal from time domain to frequency domain. In the time domain also the signal is discrete, and in the frequency domain also the signal is discrete. Now Xk, it is having real part as well as imaginary part. So Xk is equal to Xrk, so that is real part, plus Jxik. So Jxik is imaginary part. So Xik is imaginary part, Xrk is real part of Xk. Now there are two spectrum that we can this type of information that we can draw from DFT. One is we can plot its magnitude versus frequency, how the magnitude of the signal it changes with frequency or it varies with frequency, and how the phase of the signal it changes with frequency. Now in order to find the magnitude of the signal, so what we have to do, we have to square the real part of the signal plus square the imaginary part of the signal, then square root of this. So this will give you the magnitude of the signal. So this is represented by x k, that is mod, that is equal to x r square k, means square of the real part, plus xi square k, it means the square of the imaginary part, and we are adding both these parts and then taking its under root. So this will give you the magnitude, and when we have to find its phase, then we can take its tan inverse imaginary part that is divided by the real part, that will give you the phase. Now we can plot its magnitude versus frequency, that is called the magnitude spectrum, and we can plot its phase versus frequency, that is called the phase spectrum, and both these spectrums they are called the frequency spectrum of the signal that is obtained using DFT. So DFT gives a vital information that how the magnitude of the signal, what is the magnitude of the signal at different frequency components, and what is the phase of the signal at different frequency components. So how the magnitude of the signal it changes with frequency, how the phase of the signal it changes with frequency. So this type of information we can get from the frequency spectrum, because both these plots together they are known as frequency spectrum of the signal. Now coming to the properties of DFT, the first property is linearity property. So what do you mean by linear systems? The linear systems are those systems which obey the principle of homogeneity and principle of superposition. So linear systems are those. So the linearity property or the linear systems they have to obey two principles or two laws, and these laws are principle of superposition and principle of homogeneity. So what principle of superposition says? Suppose we are giving an input that is x1n and system produces output y1n, and we are giving the another input that is x2n to the same system, and the system produces output y2n. Now when we add both these inputs together, that is x1n plus x2n, and we apply these combination of two inputs to the same system, and if the system produces output y3n, then if y3n is equal to y1n plus y2n, then the system is called linear system. Then the system is called to obey the superposition principle, and if this condition does not holds, then the system does not obey the superposition principle. So a linear system it obeys the principle of superposition. And what is the principle of homogeneity? If we multiply the input by some scalar, the output is also multiplied with the same scalar. For example, xn, if we multiply it with 3, yn is also multiplied with 3. So this is the homogeneity principle. So linear systems that obey two principles. So the linearity property of DFT states that the DFT of a linear weighted combination of two or more signals is equal to similar linear weighted combination of the DFT of individual signals. So this is the linearity property. So in this case we are having two signals, one is x1n and x2n. Let x1k, that is represented in equation 5.4, x1k this is equal to DFT of x1n, and x2k that is equal to DFT of x2n. So this is given by x2n e raised to the power minus j 2 pi kn by capital N. Now when we combine these two signals and we are also multiplying these by scalars, that is a1 with x1n and a2 with x2n, then we are adding both inputs and also multiplying both inputs by different scalars and taking its DFT. Then the DFT of the combination is given by a1 x1n plus a2 x2n, because we have to take the DFT of this signal. So signal is now the combination of two inputs. One is x1n, another is x2n, and x1n is scaled by a1, x2n is scaled by a2, and combined signal is A1 x1n plus A2 x2n. Now we have to take the DFT of this combination. So we have to apply the DFT expression on this. So this is equal to summation n equal to 0 to capital N minus 1 A1 x1n plus A2 x2n e raised to the power minus j 2 pi k n by capital N. Now this is equal to summation n equal to 0 to capital N minus 1 A1 x1 n e raised to the power minus j 2 pi k n by capital N plus A2 x2 n e raised to the power minus j 2 pi k n by capital N. So we have separated these into two terms, and this gives you nothing but A1 x1k plus A2 x2k. So this is what linearity property states, that is DFT of A1 x1n plus A2 x2n, this is equal to A1 x1k plus A2 x2k. So this is the linearity property. So the next property is periodicity. So when the signal is periodic, we say the signal is periodic if and only if it repeats itself after some regular instance of time. So the signal xn, that is discrete time signal, it is periodic with period capital N if and only if x of small n plus capital N, this is equal to xn for all n, and the DFT of the signal is periodic if x of k plus capital N, this is equal to capital X of k for all k. So we can prove this. This we have to prove, because the signal is periodic if and only if it repeats itself after some regular instance of time. So by definition we know that DFT, that is x k, so this is equal to summation n equal to 0 to capital N minus 1 xn e raised to the power minus j 2 pi n k by capital N. Now we have to take the DFT of x of k plus capital N. Now on the left hand side we have replaced k by k plus n. So whatever the value of k on the right hand side, we have to replace that by k plus capital N. So what we get? We get this equation, that is x of capital X of k plus capital N, this is equal to summation n equal to 0 to capital N minus 1 small xn e raised to the power minus j 2 pi n k plus capital N divided by n. So this is nothing but equal to, because we have separated this exponential part into two parts, that is with minus sign, that is minus k, one is coming with minus k, another is with minus capital N. So this is equal to n is equal to 0 to capital N minus 1 xn e raised to the power minus j 2 pi n k by capital N into e raised to the power minus j 2 pi small n, because capital N will cancel with capital N. Now e raised to the power minus j 2 pi n, its value is always equal to 1. For if n is an integer, its value is always equal to 1. So what we get? We get summation n equal to 0 to capital N minus 1 xn e raised to the power minus j 2 pi n k by capital N. So this is nothing but capital Xk. So this is nothing but the periodicity property, which says that capital X of k plus capital N, that should be equal to capital Xk. The signal is periodic if and only if capital X of k plus capital N, this is equal to xk. Hence the signal is periodic. So the next property is circular time shift. So circular time shift property states that when we shift the input discrete time sequence xn by m samples, so that is when we delay it by m and the shift is circular. So the resultant DFT, that is capital XK, it is multiplied with e raised to the power minus j 2 pi km by capital N. Now the shift, that is m, that is in the form of delay. This negative sign indicates that it is a delay, although the shift is circular. Why here shift is circular? Because as we already see that when we convert the signal xn into xk or into x omega by using DTFT or DFT. Now what DTFT is doing, it is transforming the signal from time domain to frequency domain, and it is a continuous function of frequency that varies from 0 to 2 pi. So this is in the form of a circle. But in case of DFT, that is again in the form of a circle, but it is converted into n points. So from 0 to capital N minus 1. So it means that is discrete in nature. So the shift is, that is why the shift is in circular. Now when the delay is n plus m, means it is advanced, then the circular time shift property, it is modified. So then the resultant DFT will be multiplied with, so it becomes capital XK e raised to the power plus j 2 pi km by capital N. So the proof of this is, now we want to take the DFT of x of n minus m, that is circularly shifted by m samples. So then its DFT is given by, because we have to replace small xn with x of n minus m in the basic expression. So we get x of n minus m, that is circularly shifted by m samples, summation n equal to 0 to capital N minus 1 e raised to the power minus j 2 pi km by capital N. So let us make one substitution. Let p equal to n minus m. Now when p is equal to n minus m, so then it becomes x of p, and e raised to the power minus j 2 pi k. Now n, small n will be equal to p plus m. So small n will be replaced by p plus m. So we get this. Now you note that the summation in both the terms, it is from 0 to n minus 1. So this is reasonable because we have n points in DFT. So number of points, it will not change, it will remain n. So that is why in both the cases we are taking it from n is equal to 0 to n minus 1 in the previous case, and now we have made the substitution, then it becomes summation p equal to 0 to capital N minus 1. So what we get equal to, so this will become equal to summation p equal to 0 to capital N minus 1 xp e raised to the power minus j 2 pi kp by n into e raised to the power minus j 2 pi k m by capital N. Now this is equal to, because this xp in combination with e raised to the power minus j 2 pi k p by capital N together with summation from p equal to 0 to n minus 1, this is nothing but capital Xk. and it is multiplied with e raised to the power minus j 2 pi k m by capital M. This is nothing but the what the circular time shift property states. The next property is time reversal property. So the time reversal means when we have already done in the previous class, time reversal means when we are having a signal xn and we want to obtain a signal x of minus n. So this is the time reversal of the signal xn, means the values or the samples that are lying on the right hand side of the axis, they will come toward the left hand side of the axis, and the samples that are lying on the left hand side of the origin, they come towards the right hand side of the origin. So this is nothing but the time reversal of signal xn. So what this time reversal property states that, so this states that reversing the n point sequence in time is equivalent to reversing the DFT sequence. Now when we reverse or the sequence in time domain by n, so the resultant DFT will also be shifted by the same number or by the same time. So DFT of small x of capital N minus n. So basically what we are doing, first we are time reversal, then it is capital N minus n. So this is we are finding the DFT of x capital N minus n. Now obviously we have to replace xn in the basic expression of DFT by x of capital N minus n. So then it becomes summation n equal to 0 to capital N minus 1 x of capital N minus n e raised to power minus j 2 pi kn by n. Now again we are making substitution as we did in the previous property, but here we are letting m is equal to capital N minus n. So then it becomes capital N minus m, it has been replaced by m. So xm e raised to the power minus j 2 pi k. Now n, what is n equal to? This will become capital N minus m. Capital N minus m. So what we get then? Summation m equal to 0 to capital N minus 1 xm e raised to the power minus j 2 pi k capital N by n e raised to the power j 2 pi k m by n. Now capital N with cancel with capital N, e raised to the power minus j 2 pi k, that is always equal to 1 as long as the k is an integer value. So we substitute this as 1. So what we get, the equation becomes summation m equal to 0 to capital N minus 1 xm e raised to power j 2 pi k m by capital M. So this is nothing but equal to summation m equal to 0 to n minus 1 xm e raised to power j 2 pi k m by capital N. Now we are multiplying this with e raised to the power minus j 2 pi m, because this is again equal to 1 as long as m is integer. So this will be equal to summation m equal to 0 to n minus 1 xn e raised to the power minus j 2 pi km by n e raised to the power minus j 2 pi m capital N by n. So this is done in order to, this substitution has been made because we want to prove that DFT of x small x capital N minus n, this is equal to capital X n minus k. Now because of making this substitution, so we get summation m equal to 0 to capital N minus 1 xm e raised to power minus j 2 pi m, that is n minus k by capital N. This is nothing but, if we compare it with the expression of standard DFT, so this is nothing but equal to capital X of n minus k. So this is the time reversal property. Next property is conjugate property. This property states that if we take the DFT of the conjugate of the signal Xn, if we take the DFT of the conjugate of the signal Xn, then that will be equal to the DFT, that is capital X conjugate, that is capital N minus K. Means the DFT shifted by K and then its conjugate. So this is nothing but we have want to prove this. Now in this case, as we have to take the DFT of the conjugate of Xn, so Xn has been replaced by X star N in the basic formula of the DFT. So what we get, summation n equal to 0 to capital N minus 1 X star N e raised to power minus j 2 pi kn by capital N. So this we can replace by summation n equal to 0 to capital N minus 1 xn e raised to power, now because in the basic expression it is minus j, but we are taking conjugate out of the whole expression, so then it becomes plus j e raised to power j 2 pi kn by n, the conjugate of the whole expression. So this we can write as summation n equal to 0 to capital N minus 1 xn e raised to the power j 2 pi kn by capital N into e raised to the power minus j 2 pi n, because e raised to the power minus j 2 pi n, this is equal to 1. So we can multiply this with the expression because it will not going to affect the result. So this is equal to summation n equal to 0 to capital N minus 1 xn e raised to power j 2 pi k n by n e raised to the power minus j 2 pi n capital N divided by n, because this will again cancel, so we can multiply with n and divide by capital N. So this is not going to change the expression again. So this is nothing, when we rearrange this equation, this is nothing but capital X of n minus k, its conjugate, or we can write it as x star n minus k. This is what we want to prove. This is the conjugate property. So the last property we are covering in this lecture is circular frequency shift. The circular frequency shift property states that if we multiply the sequence xn by e raised to the power j 2 pi mn by capital N, so the resultant DFT, that will be shifted by m units. So this is what we can say, that this is the circular frequency shift, because shift is now in frequency. Now in the previous property that we did, the shift is in time, the shift is in n, now the shift is in k. So n represents time and k represents frequency. So xn, it is a discrete time signal in time domain, and capital Xk, it represents the signal in the frequency domain, it's DFT. So proof of this is DFT of, now we want to take the DFT of xn e raised to the power j 2 pi mn by capital N. So what we have to do, we have to replace small xn in the basic expression of DFT by xn e raised to power j 2 pi mn by capital N. So this is nothing but equal to summation n equal to 0 to capital N minus 1 xn e raised to power minus j 2 pi, that is common, k minus m into small n divided by m. So this is nothing but equal to, if we compare this with the standard DFT expression, so this is nothing but equal to capital X of k minus m, that is circularly shifted by m with n points. So this is nothing but that is what we want to prove. So this is the last property that we are covering in this syllabus. So DFT students, we covered in this class DTFT, how it is different from DFT, and properties of DFT.